Okay, good morning, everyone. My name is Zhao Yang. I'm a PhD student at the University of Utah, advised by Professor Stefan Nagy. Today, I'm going to present our joint work, Bin2Wrong, a unified fuzzing framework for uncovering semantic errors in binary to C decompilers. Has anyone in this room used decompilers before? Please raise your hand. Okay, but not too many. So for those of you who haven't tried decompilers or who don't know what decompilers are, they play a critical role in software assistance with the aim of reconstructing semantically equivalent C code from binary programs. The output, decompile code, is fundamental to downstream tasks that center on source unavailable components, including performance tuning on proprietary software, malware analysis on obfuscated binaries, and vulnerability discovery on commercial software. However, decompilers do not necessarily generate code that represent the original source. There can be wrong semantics in the decompile code that cause confusion to users and also lead to inaccuracy or even failures in downstream tasks that require accurate decompilation. So the question is, what factors can chiefly influence decompilation incorrectness? So to answer this question, we've surveyed and categorized publicly reported decompilation errors as shown in this table, and manually distilled them into 4 distinct factors. First, decompilation naturally faces challenges due to the lossy nature of source semantics. In binary programs, all the high-level semantic information, like variable types or function names, can be stripped away, making it difficult to reconstruct the original source. Also, different compilers generate code in their own styles. The instructions can be completely different even for the same code line. This requires decompilers to accurately recognize and reverse these different patterns. Meanwhile, compiler optimizations like loop unrolling or function inlining further transform binaries in ways that obscure their original structure and semantics. Lastly, different binary formats like ELF and MacO has their own metadata and section layouts that decompilers must handle. More importantly, many of the decompilation errors do not stem just from individual factors, but from the combinations of them. So these factors, source semantics, compiler, optimization, and binary format, not only influence binary generation, but also pose significant challenges to decompilation correctness. So preventing these decompilation errors demands thorough decompiler testing along these factors. Decompiler testing has advanced in recent years with these 4 state-of-the-art tools proposed to test decompilation incorrectness. However, as shown in this table, they only marginally explore source and compilation. They hardcode themselves to limited code constructors and with specific and certain compiler and optimizations, and they only support ELF binaries. Therefore, they have limited coverage in this broad space of binary diversity. And many decompilation errors similar to those from the previous table can remain undetected by these tools. So our motivation is, how can we systematically explore these factors and their combinations to test decompilers thoroughly? So we present Bin2Wrong, a multi-dimensional decompiler fuzzer for uncovering semantic bugs that is adaptable to any decompiler. At a high level, Bin2Wrong generates binaries by mutating source code, compiler, optimization, and binary format all together. It explores the individual and combined effects on binary diversity. To do so, we extend a powerful fuzzer, LFO++, by designing a unified multi-dimensional test case format, where the first byte indicates which compiler is selected, and the next 2047 bytes indicate which optimization options of that compiler are enabled. We extend AFL's mutation techniques like bit flip or byte flip on these 2048 compilation-related bytes. And the rest of this test case format contains the source code, which is mutated by our AST-level source code mutation. So Bin2Wrong includes out-of-the-box support for 6 compilers with more than 5,000 optimization options across 3 major binary formats and including all C code constructs. To visualize this, as you can see, Bin2Wrong begins binary generation by compilation mutation. It predefines a set of compilers to be considered and randomly select one during mutation. This also selects its target binary format. After the compiler is selected, Bin2Wrong readily enables optimization options from all the possible ones of that chosen compiler. Meanwhile, Bin2Wrong includes support for both compiling and executing P and macro binaries on Linux platforms via OS X Cross, Wine, and Darling, which have not been explored by any previous decompiler testing approach. Following compilation mutation, Bin2Wrong performs ST-level source code mutation, where it leverages libclan API to parse source code into ST nodes and mutates each node based on its ST type, including mutations like deletion, splicing, or insertion. Meanwhile, to explore source more thoroughly, Bin2Wrong specifically includes support for mutation on switch case, goto labels, string intervals, and floating point values, which have been omitted by previous decompilation testing tools. After all the mutation is done, these configurations for binary generation, including the chosen compiler, the enabled optimization options, the target binary format, and the source code is saved in a unified test case, and then Bin2Wrong compiles the binary using these configurations, and then the target decompiler generates the decompile code. Then Bin2Wrong recompiles the decompile code and executes both the original binary and the recompiled binary to compare the variable level program states. And if there's any divergence between the states, it is a signal of the decompiler generated semantically wrong code. So the test case is saved for later manual triage. This table shows the features of each decompiler testing approach. As you can see, Bin2Wrong maximizes source and compilation binary diversity and enables the most thorough evaluation on decompilation correctness to date. To demonstrate the effectiveness of Bin2Wrong, we need to answer the following fundamental questions. First, does Bin2Wrong's unified mutation attain greater binary diversity? Second, can Bin2Wrong generated binaries reach more decompiler internals? Last and most importantly, can Bin2Wrong reveal more decompilation bugs? To answer these questions, we choose 7 state-of-the-art decompilers to test Bin2Wrong with, including 6 open source ones and 1 commercial decompiler. And we choose 2 competing state-of-the-art decompiler fuzzers to evaluate Bin2Wrong against, including cornucopia that only mutates optimization options and decompiler for only mutates source code. The first evaluation result is about binary diversity. We let each tool generate 10,000 binaries and let it repeat it for 5 times. Then we calculate these binaries similarity score against the original binary across 3 different algorithms. And we calculate the mean similarity score across 5 trials. So compared to cornucopia, Bin2Wrong's generated binaries reach 6 times more to 9 times more binary diversity. And when evaluated against decompiler, they reached 15 times to 16 times more binary diversity. This result shows that by systematically exploring these factors of binary generation, Bin2Wrong's unified mutation greatly increases binary diversity. To show how this higher binary diversity translates into decompiler internals, the second evaluation result is about decompiler code coverage, which measures how much decompiler internal code those generated binaries can reach and test. So we let each tool run 24 hours per decompiler and collect all the generated binaries and repeat it for 5 times. Then we use AFO Kim-Curve to count all those executed basic blocks within decompilers and get the mean number of these basic blocks across 5 trials. So unsurprisingly, with much higher binary diversity, Bin2Wrong's generated binaries reach more code coverage within decompilers, including an improvement of 16% and 32% compared to cornucopia and decompiler respectively. And more importantly, Bin2Wrong reached more code coverage with much fewer binaries generated, including 74% fewer and 95% fewer. This demonstrates that by systematically exploring these factors of binary generation while generating much fewer binaries, Bin2Wrong can generate binaries with much better quality that can exercise more decompiler internals. And the last question we want to answer is, can Bin2Wrong reveal more decompilation bugs? So we collect all the test cases that cause divergent output between the original binary and the recompiled binary, and manually try each of them to identify their root cause. Then report these root causes to the developers and count all the total number of bugs found as well as each tool's individually found bugs. So among all the 7 decompilers, Defects found 0 bugs, Cornucopia found 10, and Bin2Wrong found 48, with 42 of them individually found by Bin2Wrong. Among the 48 bugs, 30 of them have been confirmed or even fixed by decompiler developers. And more importantly, as shown in the table on the right, Bin2Wrong finds most decompilation bugs among all decompilers. So this results demonstrate that Bin2Wrong's high diversity, high coverage binaries can test decompilers more thoroughly that can expose more decompilation errors. Many of them were missed by other tools. These are some bug examples found by Bin2Wrong, including incorrect while loop logic on -01 optimized binaries, failed string-literal recovery on TinyCC compiled binaries, and incorrect argument ordering on ELF and MacCode binaries. While I wish I could explain them in more details, due to time constraint, please refer to our paper for them. But I do want to highlight a more interesting bug found by Bin2Wrong in a commercial decompiler, Binary Ninja. So like many other decompilers, Binary Ninja decompiles a switch case statement into several if statements. But the problem is it got the wrong logic among these control flows in these if statements. So in this example, the original control flow of this switch case only executes the case 0 block, and then it breaks out of this switch case. So other code blocks are never executed. In the decompile code, however, after the block corresponding to the original case 0 is executed, the condition of another code block is also met. So there's a second code block executed, which assigns a value to a variable that should not be assigned to. This obviously causes divergence in the variable value and also incorrect control flow logic. This bug report helped the developers of Binary Ninja to identify a fundamental design failure in their control flow recovery algorithm. The developers marked the impact of this bug as high, since it's from the core of Binary Ninja and required high effort to fix it, which eventually led to an overhaul of its internal control flow recovery algorithm. So after the developers fixed this bug, they publicly wrote a blog showing the improvements and the modifications to the decompiler. This bug is not new and has persisted in Binary Ninja for a long time, but it's never detected by any previous decompiler testing approach. This further demonstrates the effectiveness of Bin2Wrong in testing decompilers, especially in finding critical decompilation bugs missed by other tools. So in conclusion, why do we need Bin2Wrong? Decompilation is critical in software and systems, but decompilation errors can cause inaccuracies or even failures in tasks that require accurate decompilation. We show that these decompilation errors are triggered by factors influencing binary generation, including source code, compiler, optimization, and binary format. But all prior decompilation approach failed to systematically explore these factors. So our solution is to generate binaries by mutating these factors all together to explore their individual and combined effects on binary diversity as well as decompiler testing. This results that our prototype, Bin2Wrong, can generate binaries with much higher binary diversity that they can test more decompiler internals and eventually revealing more bugs. That's all for my presentation. Thank you for listening. Feel free to try Bin2Wrong from our lab's GitHub repo, and I'm happy to take any questions here.